Hello! In this video, we are going to prove the following theorem. Let n be a positive integer. Then u of n is a group under multiplication modulo n. Now, let's first remind ourselves of some things. Given any two integers, a and b, we say a is congruent to b modulo n if n divides a minus b. And we have shown that congruence modulo n is an equivalence relation on the integers. So each integer has an equivalence class. And for each integer a, we represent the equivalence class of a like this. And we have defined how to multiply two equivalence classes, which is like this. And we have proven that this operation is well defined. And by properties of equivalence relations, we have that a is congruent to b modulo n if and only if the equivalence classes of a and b are equal to each other. Now, in proving this theorem, we are also going to be using Bézou's lemma, which says the following. Suppose a and b are integers which are not both 0. Then the greatest common divisor of a and b is equal to 1 if and only if there exist integers s and t such that as plus bt is equal to 1. Okay, so now let's get into proving this theorem. Now we want to prove that u of n is a group under multiplication modulo n. And the operation is given like this. Now, given any two equivalence classes in u of n, we know that we can multiply those two equivalence classes together. But how do we know that their product belongs to u of n as well? We want to verify that u of n is closed under multiplication modulo n. We want to verify associativity holds. We want to verify u of n has an identity element. And we want to verify that every element of u of n has an inverse. So let's start out by verifying that u of n is closed under multiplication modulo n. To do that, let's give ourselves two arbitrary elements of u of n. I'll call them equivalence class of a and equivalence class of b. Now, by definition of u of n, we get that the greatest common divisor of a and n and the greatest common divisor of b and n are equal to 1. Now, the whole goal is to show that the equivalence class of a times the equivalence class of b also belongs to u of n. Well, we know that the equivalence class of a times the equivalence class of b is equal to the equivalence class of ab. So really, we want to show that the equivalence class of ab is an element of u of n. And to show that, we would like to verify that the greatest common divisor of ab and n is equal to 1. And to see how we can arrive at that, let's first note, since greatest common divisor of a and n is equal to 1, then by Bézou's lemma, there exist integers s and t such that as plus nt is equal to 1. And also, since the greatest common divisor of b and n is equal to 1, there exist integers u and v such that bu plus nv is equal to 1. And then what we're essentially going to do here is we're going to multiply these two expressions together. First of all, we know that 1 is equal to 1 times 1, but we're going to substitute the first one for as plus nt, and we're going to substitute the second one for bu plus nv. And then if we expand this out, we get this. Now, as for the first term, we're going to re-express this as absu. And as for the last three terms, we're going to factor out an n. And if we do so, we get this. And now we see that ab times an integer plus n times an integer is equal to 1. So by Bézou's lemma, we can conclude that the greatest common divisor of ab and n is equal to 1. And this tells us that the equivalence class of ab satisfies the requirement to be an element of U of n. And we know that if we multiply equivalence class of A and equivalence class of B together, the result will be equivalence class of AB. And therefore, the equivalence class of A times the equivalence class of B is an element of U of n. So this shows that U of n is closed under this operation. Now let's verify that associativity holds. To verify associativity, let's give ourselves three arbitrary elements of U of n. I'll call them equivalence class of A, equivalence class of B, and equivalence class of C. To verify associativity, we want to show that the following equality is true. We want to show that this happens. So let's start out by writing the left-hand side. Now, by definition of multiplication modulo n, the equivalence class of A times the equivalence class of B is equal to the equivalence class of AB. And then applying the definition again, this is just the equivalence class of AB times C. But we know that the associative law holds when we're just multiplying integers. So we can move these parentheses around BC. And then applying the definition of multiplication modulo n, we can rewrite this as the equivalence class of A times the equivalence class of BC. And then applying the definition again, we can rewrite equivalence class of BC as the equivalence class of B times the equivalence class of C. And so, through this chain of equalities, we have verified that this happens. So this shows that associativity is true. Now, let's show that U of n has an identity element. The claim is that the equivalence class of 1 is the identity element of U of n. And to show that, let's first verify that the equivalence class of 1 is an element of U of n. To show that, we would like to show that the greatest common divisor of a 1 and n is equal to 1. But this follows from Bézou's lemma, because 1 times 1 plus n times 0 is equal to 1. So we see that 1 times an integer plus n times an integer is equal to 1. And that tells us that the greatest common divisor of 1 and n is equal to 1. And this tells us that the equivalence class of 1 satisfies the requirement to be an element of U of n. Now we want to show that the equivalence class of 1 is the identity element of U of n. And to prove that, let's give ourselves an arbitrary element of U of n. I'll call it equivalence class of A. And to show that the equivalence class of 1 is the identity element, we want to show that the following equality is true. We want to show that this happens. And to see how, we observe the following. First of all, by definition of multiplication modulo n, this is just the equivalence class of A times 1. But we know that if we do A times 1, we're just multiplying integers, so this is just the equivalence class of A. Similarly, A is just equal to 1 times A, so this is just equal to the equivalence class of 1 times A. And by definition of multiplication modulo n, this is the equivalence class of 1 times the equivalence class of A. And so, this chain of equalities shows that this happens. And therefore, the equivalence class of 1 is the identity element of U of n. And now we're going to show that every element of U of n has an inverse. So to prove that every element of U of n has an inverse, let's give ourselves an arbitrary element of U of n. I'll call it equivalence class of A. And from the definition of U of n, we get that the greatest common divisor of A and n is equal to 1. And by Bézou's lemma, since the greatest common divisor of A and n is equal to 1, that tells us that there exist integers s and t such that as plus nt is equal to 1. But notice, we have that s times an integer plus n times an integer is equal to 1. So applying Bézou's lemma again, this tells us that the greatest common divisor of s and n is equal to 1. And this tells us that the equivalence class of S satisfies the requirement to be an element of U of n. And the claim is that the equivalence class of S is the inverse of the equivalence class of A. And to show that, we would like to verify that the following equality is true. We want to verify that this happens. So, to see how this happens, well, first note, if we take this equation, subtract nt to the other side, and subtract 1 to the other side, then we get this. So n divides a minus 1. But according to the definition of congruence modulo n, this tells us that as is congruent to 1 modulo n. And from what we stated earlier about equivalence classes, this implies that the equivalence class of as and the equivalence class of 1 are equal. And now we're in a pretty good position to show that this equality happens. Firstly, by definition of multiplication modulo n, the equivalence class of A times the equivalence class of S is equal to the equivalence class of AS. And we know that the equivalence class of AS is equal to the equivalence class of 1. Again, I'm going to write equivalence class of 1 is equal to the equivalence class of AS. Now, we know that the commutative law holds when we're multiplying integers, so we can rewrite this as the equivalence class of SA. But then, according to the definition of multiplication modulo n, this is the equivalence class of S times the equivalence class of A. So, this chain of equalities shows that these three guys are equal. That's exactly what we wanted to show. So this shows that the equivalence class of S is the inverse of equivalence class of A. And so, this verifies all the requirements for U of n to be a group under multiplication modulo n. And so this completes the proof. Now another thing is that U of n is an abelian group under multiplication modulo n. In other words, we can verify that the commutative law holds for U of n under this operation. Because if we consider two arbitrary elements of U of n, call them equivalence class of A and equivalence class of B, well then, if we multiply equivalence class of A and equivalence class of B together, well then, according to the definition of multiplication modulo n, this is the equivalence class of AB. But since we know that the commutative law holds when we're multiplying integers, we can re-express AB as BA. But then, according to the definition of multiplication modulo n, this is the equivalence class of B times the equivalence class of A. So we have shown that the commutative law holds for any two elements in U of n. And this shows that U of n is an abelian group under multiplication modulo n. And so yeah, that's pretty much it for this video.